So hello and welcome everybody to another edition of the Journey Down the Clackamas. This is the 8th session. I'm Liz Gilliam, a geomorphologist and the Restoration Program Director for the Clackamas River Basin Council. So very excited about tonight's subject matter. I hope everyone finds it as fascinating as I do. Joining me tonight are Todd Bartlett, the CRC, the Clackamas River Basin Council Board Chair-elect, and Ari Sindel, who is the Clackamas River Basin Council's riparian specialist. And they are helping me tonight with the technical aspects of the program. There's a couple just logistics to cover before we get started. Well, this isn't a logistic, but the Clackamas River Basin Council is celebrating our 25-year anniversary this year. Since our founding in 1996, the CRBC has worked as a non-governmental group of stakeholders to protect and improve the Clackamas River Basin and its tributaries. So our mission is to foster partnerships for clean water to improve fish and wildlife habitat and the quality of life for all those who live, work, and recreate in the Clackamas watershed. Sorry, on behalf of the Basin Council, I'd like to thank our gold sponsor, Clackamas Water Environment Services, or WES, and we also thank our bronze sponsors, Clackamas River Water Providers, and the Geological Society of the Oregon Country, GSOC. And thanks also to the many individuals who have donated to support this conference. We continue to seek support, keep it free for everyone to involve. So those are tax deductible. So if you feel motivated, you can find a link to provide a small donation on our website. So the Clackamas River Basin has been occupied by Native peoples for millennia, and it is originally the territory of the Clackamas, Chinook, Molalla, Kalapuya, and other peoples, and is currently recognized as lands of the Confederated Tribes of the Grand Ronde, the Confederated Tribes of the Warm Springs, and belongs to other Native peoples who may not be federally recognized. We thank those who came before us for their stewardship of these lands and waters, and those who continue to steward them now and in the future. So we are gathered for this journey down the Clackamas to learn in-depth information about the basin and its connections to Oregon as a whole, and to connect with each other so that we can support our mutual efforts to protect and improve the Clackamas River and its tributaries. CRBC is partnering with the Environmental Learning Center at Clackamas Community College. Any workshop attendee will receive a CCC Continuing Education Unit, or a CEU, and can also request a signed certificate of completion for each session. So if you would like a certificate of completion, add your contact information to our Journey Down the Clackamas networking Google sheet and indicate you'd like a certificate in the G column, and we'll forward your contact information to Clackamas Community College. So a few ground rules before I introduce our guest this evening. Please, throughout the presentation, please keep your microphones on mute unless you're invited to participate. And you can keep your cameras off if you'd like. That will help us save bandwidth for our presenter and greatly reduce the carbon footprint of our meeting. We'll hold a Q&A session after the presentation. So please either type a question in the chat, or if you want to, you can just type, I have a question, and we will ask you to unmute and you can ask the question yourself. So also throughout this evening, feel free to send direct chats to your friends you're seeing in the participant list. The presentation is being recorded. So with that, I will start our presentation for this evening. So our presenter is Dr. Peter Wampler. He is a broadly trained environmental geologist, geomorphologist, and surface water hydrologist with a background in both academic and government regulation of mining and stormwater. He received a master's and PhD at Oregon State University. His PhD was work on human and climatic-induced changes along the Clackamas River. And he has completed extensive research on the geomorphology of the Clackamas. So it'll be great information this evening. He is now at Grand Valley State University. He joined there in 2004, and he's been working with undergraduate and graduate students on applied geoscience research. And he has traveled to Haiti numerous times since 2007 to work on water resources issues and safe water interventions. And he's led students on multi-week study abroads to Haiti, where students engage in service learning projects, ecotourism, and water resources investigations. He's also currently the co-leader of an honors initiative called Making Waves About Water that focus on interdisciplinary collaborations in water. And I'll share links to both of those programs in the chat. He has mentored dozens of students working on research projects in Michigan, several US states, as well as in Haiti and Ghana. And lastly, he loves to kayak and raft on rivers, hike to unexplored places, and generally look for adventures. So I would just like to say thank you for your presentation. We rely on your research all the time doing work in the basin, and it's been an extremely useful source of data to help us understand and plan for projects. So I'd like to welcome Peter. Thank you. Go ahead and share your screen.
All right, thank you very much, Liz. I assume you can see my screen now. You're all good? Good. Yeah, so thank you very much. It's been really fun. I appreciate you inviting me to share about some research I did a long time ago when I got to dig into my PhD research and kind of get up to speed again with a river that I really love a lot. And I share your love of the Clackamas, and that was fun to think about it more again. So this is what we're going to talk about. I'm going to do a kind of a brief summary of the geologic setting, and I know you've heard some about that, but I'll mainly focus on kind of its connections to geomorphology and the way the river functions. And I'm mainly going to focus on the lower river, but I will touch on the entire watershed briefly. And then we'll move on to talking about how humans have interacted with that geologic setting and the geomorphology of the river, things like dams and urbanization and other impacts that have sort of changed the system and tweaked the way it behaves. And then lastly, I'll talk about the way sediment is transported in the river and how the dams have affected that. And then some projects that are being done right now to augment sediment transport on the river below River Mill Dam. So hopefully you'll learn more. And if you have questions, for sure, put them in the chat or write them down and we'll answer them at the end. So yeah, the geology of the Clackamas over the long term, is really determined by the bedrock. And the bedrock in most of the Clackamas, I'll talk about more in a minute, but it's millions of years old, and it sets the stage for the river at its base level, and then everything else is sort of superimposed on that. And so it has a pretty big influence on the vertical erosion, the lateral erosion, and the differences in the way the river erodes from the headwaters down to the Willamette. It changes dramatically along its route. And a lot of that is actually bedrock related and geology related. And then superimposed on that are these terraces, which you've all have seen as you've driven around Estacada and in the area around the Clackamas. You've probably seen large amounts of gravel stored up on the edges of the valley. And those are terraces from the Clackamas River. And as I'll explain, some of those are quite old, they're quite extensive, and they really represent a very different climatic regime for the Clackamas than currently exists. And so that's a very interesting part of the story. And then more recently, in the last thousands of years or so, last 1,000 years, the river really has been largely fixed climatically, but it has these fluctuations that happen over long or short time frames due to climate, but also due to human changes like dams and gravel mining and logging and urbanization. So I'll touch on a little bit of those and how they impact the behavior of the river. Okay, so first a bit of geology review, if you've already probably heard about this a little bit, but this is the basin, and this is the geology of the entire basin. And it's really divided up into 3 parts, and it's in 3 different geologic provinces. So the upper part of the basin is in what's called the High Cascades province, which you probably heard about, but it's characterized by young lava, quite different than the middle part of the basin, which is older lava. And so that young lava tends to be very porous, and it tends to have different runoff characteristics than the stuff down below. And you'll see there's this kind of stippled is landsliding. So it's somewhat prone to landsliding just because of the steepness of the terrain and some of the recent volcanism. So then as you move downstream, the story gets a little more complicated. You have what's called the Western Cascades, and they're this ancient volcanic rock that is much more weathered, much older, tends to be less infiltration, the runoff characteristics are different. And then you have this funny purple unit toward the middle of here, and that's the Columbia River basalt exposed along the river. And that actually is quite a durable unit and doesn't erode very quickly at all. So it sort of fixes the position of the river and doesn't allow it to move a lot laterally or vertically, even though it's in this unit that in other circumstances would be pretty erodible, but it isn't very erodible because of that small exposure of Columbia River basalt. And then as you move into the lower river, which is going to be the main thing I'm going to talk about, you move into the Willamette Valley province and you get widespread deposition of sediment that came out of the Cascades. And as we'll learn, a lot of that sediment that came out of the Cascades came out at the end of the last ice age, and it was basically released from probably big glaciers that were in the mountains, and then it made its way down the valley and was deposited in the lower basin, in the lower Clackamas Basin. And it did it in a really interesting way over a period of tens of thousands of years. So that's where we're headed next. So you might recognize this exposure if you floated down the Clackamas. This is the lower Clackamas. And this is just a typical exposure of some of these terrace or stored gravels that are adjacent to the river. And these are actually a terrace type called a strath terrace because the gravel is actually sitting on bedrock that's above the river itself. So this is actually an elevated piece of bedrock with gravel deposited on it. In this case, probably of 2 different ages, one that's about 22,000 years old, and then some younger gravels on top of that that are about 10,000 years old. And so that's a pretty typical sequence that we see all up and down the Clackamas, that bedrock exposure, sometimes elevated as a terrace like that, and then an older unit, and then a younger unit on top of that. So this is what the geology map I created for my PhD. And it pretty much was a couple of things that were kind of amazing when I first started looking at this. One is the extent of these terraces. These are huge terraces of very flat-lying gravels that were immediately obvious that they were big terraces. They were above the river by quite a distance, 150 feet, 200 feet in some cases. So I was immediately drawn to these to figure out, okay, how old are these? And it took us a while, but we got some dates on these, and we figured out that this purple unit up here that sits up along the edge, we dated at 22,000 years roughly. And then this tan unit, which is inset into the purple unit, is about 10,000 years old. So what we're seeing here is during the purple time, 23,000 years ago, there were glaciers up in the mountains that were melting away, and there was a faucet of sediment that was turned on, and water, both, and it was allowing massive transport of gravel. And it created, during this purple time period, the entire valley was full of gravel, for a distance of 8 kilometers or more across this valley. And so at the time, it probably looked like an outwash plain that you might see in Alaska today. So just a massive outwash plain, glaciers up at the headwaters, just pumping out sediment, pumping out water. And then as the glaciers melted and there was less ice to melt, and then the sediment faucet got scaled back about 10,000 years ago. And so there wasn't as much sediment available, there wasn't as much water, and so the floodplain got smaller. That's this tan or brown time. So it was still probably a braided river, very large floodplain, still a couple kilometers wide, but it was smaller than it was 10,000 years before that. And it was, so that period of 10,000 years was a time where the glaciers were getting smaller and you were just reducing that sediment output. And then more recently, it's done the same thing. It's actually gotten narrower and it's incised into that the brown unit to form this 650 plus or minus year old floodplain, which is in the yellow. And so that's sort of the meander zone in which it can move within the last 650 years or so. Parts of that it can move easily now, and parts of it are fixed because of erosion. So to summarize how that works, so basically 22,000 years ago, you had these glaciers up in the Cascades. They were melting away because the ice age was ending, and they were pumping out sediment, pumping out water, and that was causing pretty dramatic filling deposition that planed off a huge area and deposited a huge area of gravel. And then as that got turned down a little bit over the next 10,000 years or so, the amount of gravel was reduced, the amount of water was reduced, and that meandering or that braided floodplain got smaller. And so it got narrow, and that's that kind of tan unit on the map. And then more recently, the same thing has happened. You've reduced the sediment, reduced the water, and that's caused it to get even narrower, less width to the floodplain and more restricted in where it can meander. So that's the story of the Clackamas over the period of 22,000 years or so that kind of has created this really unique set of terraces, which I have never seen any terraces as good as the Clackamas. They are some of the best terraces I've ever seen anywhere I've worked. So you have a great set of terraces to look at. So this is the exposure in the Estacada gravel pit, and it's where we did the sampling to get the dates. So we actually were able to find little sand lenses in these gravels, and then through a lot of looking and a lot of meticulous picking at them, we were able to collect enough of this carbon to actually do a carbon date and get several carbon dates that allowed us to understand that these are 22,000 years old and these are 10,000 years old on top. So that's pretty consistent, and I'm not sure if people have dated it since then, but I think at least some dates have been gotten since then that are consistent with these dates. So when you look at a cross section like this would be near River Mill Dam, roughly, at McIver Park. So you've got the bedrock that's lying underneath all this stuff, which in this case would be Western Cascades volcanic rocks, the red with the round boulders in it. And that is overlain by Sandy River mudstone, which is exposed in most of the lower river. And then on top of that, in the upper parts of the valley, you've got this old terrace unit, and on top of that you have a younger 10,000 year terrace unit, and then inset into that you've got all these younger terraces. Like at McIver, you have maybe as many as 6 or 7 or maybe even 8 terraces that are preserved within that valley, and those are all representing essentially continued decrease in sediment and continued kind of decrease in width. So the river's gotten more and more restricted in its lateral migration, and it's gone down vertically. So the story of the Clackamas is essentially narrowing and deepening over the last 22,000 years, pretty much. And this is just another way to look at that happening and with another set of data. So this is elevation data on those terraces, on those flat surfaces that I just mentioned. And so the purple ones here are on that oldest surface that's on the edge of the valley. And so it is the highest one, the oldest one. And it had a slope of about 0.5%, so relatively steep. And so you compare that to the modern slope, which is the yellow here, and it's about half of that slope. And so this is the amount of incision from 22,000 years ago to today, about 200 feet of incision. So pretty dramatic, pretty fast rate of incision. And I'll talk about kind of why that might be. But and you can see the incision is not the same up by River Mill Dam as it is down below. And that's probably a function of bedrock to some extent, because up here you have a hard bedrock, you have the volcanic rock, and down below you have a much softer bedrock. And you also have deposition of sediment down here, which might be impacting that. So pretty consistent story. And then when you put all that together, these guys, Leopold and Wollman, came up with a way to understand the way rivers are shaped, basically based on the slope of the river and the amount of water flowing in the river. So the y-axis here is slope of the river, and the x-axis is the amount of water flowing. And so if you go back to when the glaciers were active, greater than 22,000 years ago, you had a braided system, very big, very wide, pretty steep slope. That would be up in here. And then over time, as the amount of flow decreased, the amount of melting glaciers decreased, you tended to move to the left and the slope decreased. And so you end up kind of where we are today, which is a combination of meandering forms and probably braided forms in certain sections. So a mixed, kind of mixed morphology. And the interesting thing is that this pattern that we see in the Clackamas of narrowing and vertical incision is present in the Molalla, it's present in the Saniam, it's present in the South Saniam, but it's nowhere near as pronounced. It's present, but the amount of incision is much more dramatic in the Clackamas. But the same pattern of this older terrace and the younger terrace, you can see that all up and down the valley. So the same event that created those big, huge gravel deposits in the Clackamas was happening in the Molalla, North Saniam, and the South Saniam, and other drainages along the Cascades. So it was a regional event, a regional melting event, a regional climate event, but something happened unique to the Clackamas that caused the incision to accelerate much more quickly. So this is what the incision rate is comparing those other drainages and the Clackamas. So you can see compared to say the Coast Fork of the Willamette, this is about 8 times as fast in the Clackamas as the Coast Fork. So dramatically faster, about 3.5 times the Mackenzie. So just much quicker incision rate or vertical erosion rate. And I'll kind of come to why that might be in a minute. There's competing theories in why that might be the case. But so to summarize all that story into a succinct couple bullets, there are these 2 really prominent terraces for the Clackamas River. One is 22,000 years old. One's about 10,000 years old. Both of them were created as the glaciers were melting and as they were releasing all of their sediment, and it was depositing in the Clackamas Valley. And then as that global climate change reduced the amount of glaciers and the amount of sediment coming in, the river began to narrow and deepen. And that's kind of where we're at today, is it's narrowed and deepened. So since about 650 years ago, plus or minus, there's some incision happening, but largely the river's fixed within this relatively fixed meander belt, and it can move back and forth across that meander belt depending on if it's up against a cliff or not, and if there's sediment to move around or not. So, and this number is approximate, obviously, ranges from 8 to 3.5 times or so faster than these other cascade drainages. And I'll tell you the punchline is, I think at least the reason for that is that the mouth of the Clackamas has had a different elevation in the past than it currently does. Either because the Willamette Falls progressed across the mouth and changed the location from above to below the falls, or the location of the mouth of the Clackamas moved to above or below the falls on its own. But for some reason, the base level changed dramatically, and either because of an interaction with the Willamette Falls or something else that I haven't figured out yet, or someone else hasn't figured out yet. So pretty much it's got this dramatic incision signature, which is unique. It's not like other drainages. And then it's created this kind of combination form where you've got meandering sections that are clearly looking like a meandering river, but then there are other sections like near, well, the section through McIver Park, where there's clearly braided system happening. So you got both forms in the same place. Okay, so moving on to from geology, hopefully you have a good sense of the background and kind of why the river behaves the way it does, how it responds to sediment, why there's sediment there in the first place, where some of that sediment comes from. And now we're going to move on to talking about how changes to the system have impacted that existing kind of framework, or that tapestry of what's going on. And one of the biggest changes, obviously, is the dams. So multiple dams on the Clackamas. I'm really only going to focus below Rivermill because that was the main focus of my PhD research. We certainly did look at other parts of the river, and others have looked at it a lot more than I have. But I primarily focused below Rivermill Dam because my work was related to the relicensing of that particular dam. So this is below Rivermill, and this is that volcanic breccia that I mentioned. A breccia is just basically a volcanic rock made up of fragments of rock. And so you could think of it as basically it looks like concrete with big boulders in it. And it's called the Sardine Formation, and it's an amazingly durable rock with really big rocks in it that get liberated, and then they become part of the river system. And that'll come into the story in a bit when we're talking about grain size and the size of the rocks in the river. But that bedrock on the upper part of the river is what the river's flowing over, and it doesn't really have, it's not easy to erode. So it's pretty fixed at that location. It doesn't tend to move out of that location very easily. And you'll notice in this picture, there isn't a lot of sediment. There's not a lot of sediment stored here. And so certainly that is at least in part because of the construction of River Mill Dam and the interception of all the sediment that was formerly moving along the river that got caught behind River Mill and North Fork and other dams in the system. So one of the things that could change if you build a dam on a river is you could potentially change the flow. It turns out that River Mill is a run-of-river dam, so it doesn't really change the flow that much. North Fork is slightly larger and has slightly more influence, but this is the peak flows for the Clackamas since 1909. And I did put a trend line on this, and the trend line is basically completely horizontal. There's no real increase or decrease in this peak flow data. Now, that doesn't mean there's no changes. I mean, it looks like there's been a few less floods recently. It could be that low flows are different, could be that medium flows are different. But if you're just looking at peak flows, there really hasn't been a large change that's discernible, in the pattern. But there has been this massive change in sediment flux. So we talked about the system that had massive sediment coming down from glaciers. Well, even before the glaciers were done, before the dams were built on the river, there was a lot of sediment being transported by the Clackamas, and very large sediment. And so when you constructed the dams, all of that was prevented from moving, and it had a dramatic influence on the amount of sediment and the size of the sediment, both. So basically, before the dams were constructed, you had highly variable sediment moving in the river depending on big floods. Big floods transport a whole bunch of sediment, and then you might have a dry year where you don't transport any sediment at all. But that was a typical pattern for the Clackamas. And then you build the dam, and essentially below the dam, there's no sediment transport. So what happens is you create what's called hungry water, and below the dam, you have no sediment to transport, but you have water that has energy, and that energy wants to transport sediment. And so it either erodes the bed or it erodes the banks to find more sediment. And so typically what happens over time, the bed of the river below a dam will excavate vertically or in size. And that can be uniform like that green line shows. It could be, usually it's more near the dam and then less downstream, which is kind of what we see for the Clackamas. But this is highly dependent on the amount of sediment that was being transported before the dam was constructed, and the bedrock below the dam and its ability to resist erosion. So does this happen? Is this happening in the Clackamas? This is data from the Gage at Estacada, and it does seem to show some lowering of the datum for the Gage, basically. So you've got essentially a lowering of about 0.3 meters at the Gage. So does seem to be consistent with some amount of lowering. So one of the things I had to do for my PhD was to try and demonstrate the impacts of River Mill Dam on the Clackamas River. And in order to do that, I had to try and figure out what it looked like before the dam was built. And one of the most frustrating things was trying to find data that was prior to 1911 so that I could demonstrate what the river looked like. And I searched and searched and searched for about 2 years actually before I found this gold mine that my wife and daughters are holding in my backyard. This is a 6-meter long map of the Clackamas River surveyed in 1908. And I found this just by chance in PG's office. It was a vellum, that I was able to make a copy of, and it was a gold mine because what it did is it had elevations along the entire river that were pre-dam. And so it gave me the ability to go back in time and compare pre-dam conditions to what I measured in roughly 2003 is when I measured the data. So I was able to take that data from that map and basically figure out a longitudinal profile for the entire river and see how it had changed between 1908 and essentially 2000, which is when I did my analysis. And what we found is that essentially the upper river near the dam was, for the most part, degrading or incising or going down. And then toward the middle of the river, there was essentially no change. And then in the lower part of the river, it was actually aggrading or getting higher. And so that's pretty much consistent with there being, hungry water here, removing sediment up here, or moving bed here, and then there being a transition stage, and then actually some of that sediment moving to the bottom of the river and getting deposited. So that it's consistent with that at least. So one of the things that we found, though, when we did the surveying of the river below the dam is that not only did it go down, but there was a really interesting sort of cyclic pattern of deep pools below the dam. And so it's unclear if that was because of the dam or if that was happening before the dam was constructed. The data was not clear on the maps, but they're certainly there now. There are these deep pools, 30, 40 feet deep in some cases. And it's possible those are a function of the erosion that's happening in the bedrock below the dam. And this is what they look like. So I did some pretty detailed measurements below the dam. This colors on this map represent elevation, both underwater and above water. And so you can actually see these divots here are actually very deep pools in the bed of the river. And so those deep pools, it's unclear if those were a historic feature that were actually there before the dam was built, or whether they might have been there, but maybe not as pronounced. But they certainly were pronounced when I measured them in 2003 or so. And so this is those again. So the question is, if we were to start to add gravel below the dam, will these fill up? Eventually, will this bottom of the river actually become a gravel bed river, or has it always been a bedrock river and it won't convert back again? These are some questions we don't know yet, and we'll find out as we do more gravel augmentation that I'm going to talk about in a little bit. So one of the other impacts from hungry water that comes out of a dam with no sediment below river mill is that the water has energy but no rocks to carry. And so what it does is it acts like a winnowing force. So if you had like wheat in your hand and you were blowing on it, it would blow all the chaff away because it's light. Well, the same thing would happen with the small granules of sediment. You have water that's flowing over it that has a lot of energy, and it has the energy to transport all the small particles, but not energy to transport big particles. So what we expected to see when we looked below the dam is a coarsening of the bed, and it did look very coarse. This is taken in 2002 below the dam, and you can see there's really big rocks here. And so the question was, is this happening because of the dam? Can we demonstrate any kind of pattern of coarsening near the dam, and where does it end below the dam? So we did a whole bunch of measurements, and each one of these dots represents data we collected, actually going out and measuring a whole bunch of rocks to establish essentially an average grain size, what's called a D50 of that spot in the river. And so these diamonds represent whole bunches of places where we measured the rocks on the surface. And what we found is that below River Mill Dam, there is this pretty significant increase in the average size of the rocks. And so that was certainly partially probably attributable to the dam being there and it causing that winnowing effect and that coarsening and that bed armoring effect. So this green line is what you would see in a sort of a typical river. And so we're seeing this kind of a deflection in the trend, if you want to call it that, below the dam that we think represented that hungry water and that winnowing effect below the dam. It could also be that some of it is due to the geology. This sardine formation is that formation I mentioned. It has the big rocks in it. So that's a bit of a confounding geography piece there. So this is a map to illustrate that. So River Mill Dam, and then this red color on here is this volcanic unit that has rocks like this. This rock is the size of, what is it, small car maybe, very large rock. And it came out of the sardine formation somewhere in here. Actually, that one's actually much up in here, actually. So the question is, does some of our data that we collected about surface size of the rocks, is it being influenced by the fact that these big rocks are around coming out of this sardine formation? And it's certainly possible, and it certainly might have skewed our data, but I still think there's a pretty significant signal for a coarsening of the bed. And that's what gave rise to this idea that we needed to come up with a sediment management plan for the Clackamas River that would start to replace some of that rock that's been intercepted by the dam. So just to summarize those things we saw really measurable impacts both in size, grain size, and incision, about 1/3 of a meter. And then we got this strange deep pool effect that's going on. The channel gets narrower, and we got a lot more exposure of bedrock. And then below that, it gets a little more complicated, probably general incision for about 8 kilometers or so. And then probably differences in the way the channel behaves below that. So the last thing I want to talk about is this plan that we came up with as I was finishing my PhD. I worked with McBain and Trush, which is now McBain and Associates, to develop a sediment management plan that would then become part of feeding the hungry river below Rivermill. And so back in 2003, we did some pilots, study of that. We put a truckload of rock in the river with some tracer rock in it so we could see how it was going to move. And then we used that to help develop this plan. And then that plan was incorporated into the license for Rivermill. And so it began being implemented in 2016. And so they're actually adding thousands of yards below the dam to augment or to add gravel below the dam. So this is the river below Rivermill. There's Rivermill Dam, and then the place where they're adding gravel is right here. And Estacada Rock Products is right there. And so they're getting the rock actually from this 10,000-year-old terrace that I mentioned earlier. And they're placing it right here. It's about 260 meters below the dam in a location that is easily eroded during big floods. So it's intended to erode. And part of the reason for that location, at least for me anyway, was that there was historically material placed there when they built the dam, and that material is completely gone. So clearly the river can process that material and it can move that material away from that spot. And so we thought it was a good spot to add gravel and have the river reincorporate it so they can kind of rebuild some of the geomorphology that had been potentially impacted by the dam. So this hashered area is all that terrace. So it holds almost 2 million yards of gravel available for augmentation that's owned by PGE. And so they have plenty of resource available to do this augmentation. This is the exposure in Estacada rock, but it's essentially the same rock that's nearby on the PGE property. So they basically, the plan was to mine that material up here on this terrace on property owned by PGE, and then move that material down to the bar, and then place it in the river or near the river and have the river erode it basically. So during summer low flow, you place the material. That material is at a position such that when the river comes up and floods, it will mobilize and become part of the sediment transport and then be deposited downstream. So during flows like this, you would be getting probably some transport of gravel, and so that would be eroding off of that bar and being incorporated into the river and then feeding that hungry river so it could rebuild bars and rebuild structures down below. So these next few slides are actually from Jeff Hales, so I think is actually here tonight, and McBain Associates. They're the ones actually implementing this plan that we developed. But some really cool stuff. They added, this is a picture from where they added 8,000 yards on that bar. And this is that same area from another perspective. But this has been going on since 2016. So these are water years on the top, which is a little confusing for people not used to it. But so in 2016, they placed essentially 8,000 yards, and only 800 of that was recruited, which means that's how much the river actually eroded. And then the idea when the original plan was to then replenish that amount or whatever was recruited. And so you're basically feeding the river whatever it wants based on the hydrograph for that year. So in a year where you've got a lot of flow, you feed it more gravel, and a year that you don't get a lot of flow, you don't feed it much gravel. So that's pretty much what they did. And so to date, they've added about 38,700 cubic yards. Now, I don't know what they did in 2021. Maybe Jeff can share that at the end. But of that, about 18,700 yards has been recruited or actually incorporated into the river. And so that's moving downstream and becoming habitat. So this is 2018, and after that, this flood event, you can see it took away that bar basically and moved it downriver and incorporated that into the downstream. This is what the picture looked like in 2020. So they had placed material, but 2020 was a pretty quiet year hydrologically. So I'm not sure if this has moved off again after that, but this is the kind of changes they're seeing downstream. So you can see this is the same location, 2013, 2018. And if you look closely, this has much larger sediment than the lower picture here. You can see how fine the sediment is here. So you're basically changing that average size of grains to smaller, and which is more compatible to fish moving with their tails, to macroinvertebrates sometimes living in them, and just in general better for habitat. So a similar picture, this is the same location, 2013, 2018. You can see much finer gravel here on the right, much coarser gravel on the left. So that's what this whole plan is intended to produce, is more fine gravel and better distribution of these gravel bars. So just some take-home points. So the bedrock, as I said, is eroding rapidly, both laterally and vertically. Not so much laterally at the moment, and these terraces, these huge terraces, are evidence of this long-term climate change that's happened on the Clackamas, from being a very sediment-rich, high flow regime to sediment poor, relatively low flow regime compared to what it was during the Ice Age. And then these human-induced changes like the dams and other human-induced changes are superimposed on this big system of sediment being deposited. And then the incision and armoring, we're seeing some ability to reverse those effects. The program has just started. Hopefully we'll be able to see more and more as that program's implemented, and be able to see positive changes towards reversing incision and reversing that armoring that we see below the dam. And last thing I'll say is I would love to get out there and reproduce some of the sections that I did back when I did my PhD. We did a ton of surveying, and if anybody wants to get out there and reproduce some of that, I would love to get out there. It'd be fun to do it like in 2023. It'd be like 20 years after I was out there. So, all right. So thanks especially to Jeff for sharing his data with me and McBain Associates. But happy to entertain any questions you have about the Clackamas or geomorphology or anything about the Clackamas that I know anyway. So thanks.
Thank you.
So Peter, this is Todd Bartlett. There were some questions in the chat. Paul asked, are there any similar terraces in Portland alongside the Willamette or Columbia?
It's a good question. There are terraces that not as well preserved for sure, and not so much along the Willamette. Those terraces are not preserved along the Willamette itself that I know of anyway. They would have been largely, but I don't know along the Columbia how preserved they are. That's a good question. I don't know the answer to that. So, was there another question? Was it?
Yeah. So Dan asked, what's the grain size of the gravel that's being put into the river, and how does it compare with what is downstream?
That is an excellent question, and it's one we debated about a lot when we designed this augmentation program. And I think, Jeff, if he's here, he can correct me if I'm wrong, but what we had proposed was to add the full range of grain sizes, not to restrict the grain size, so that the river could basically distribute it hydrologically, so that it would have the large framework rocks as well as the really fine materials to distribute through the system. And so the original design was to introduce all grain sizes, more similar to what would happen sort of naturally if you were eroding that terrace naturally, as opposed to trying to pick a certain grain size and have it only transport that size. Does that answer the question?
Yeah, I think so.
Yeah.
Peter, you're correct on that, Peter. This is Jeff Hales.
Hey, Jeff, thanks.
Hey, yeah. And the main idea was also we wanted to restore or help improve geomorphic processes and not just cater to either biology or geomorphology together. So the whole native grain size and just using the natural distribution was selected, and that's what we're using.
And the idea was that the river would do the hydrologic sorting for us, in essence, putting it where it needed to be. I think was the idea, at least. You know, and the larger framework rocks would end up in the bottom of pools and things like that to help fill those areas, and the smaller ones would accumulate in bars that would be more effectively used by, you know, salmon and things like that.
And I'm assuming the idea behind all of this, Peter, is that you're trying to create what the river would have naturally been had not the dam been placed there and interrupted the flow and the erosion that was natural.
Yeah, you're basically trying to rebuild some of the bars that probably have been removed because of this hungry water. You know, the bars have been eaten basically, and they're no longer there. So yeah, you're trying to provide the framework to rebuild those bars, which, you know, improves temperature, it improves habitat, it improves potential spawning habitat. All those things are potentially improved if you have more of those bars available.
Okay. A question from Glenn: how important is bank stabilization / riprap hardening around developments in changing processes in the lower Clackamas?
I mean, I personally feel like any kind of bank protection is not good. I mean, I think the river needs to be able to process the materials in the banks in order to have its migration, you know, within a certain meander migration path. It should be able to migrate and meander. That's part of a natural and functioning system like the Clackamas. So if you fix one side with concrete or with riprap, then you know, the system is not able to function the way it was naturally functioning. So you end up getting maybe deeper water in that location, faster velocities, none of which would be, you know, favorable to organisms that were used to it being able to meander and create its own structures and create its own depths and things like that. So all those artificial structures tend to create habitats that are not necessarily similar to ones that would have been there had they not been there, I guess is my perspective.
So somebody had a follow-up question around your comment around the Clackamas River mouth elevation change that you mentioned, and did it outlet at some point farther north? I think you were not sure about that piece, but.
So yeah, there's, you know, I looked pretty hard at the topography and stuff and tried to put together the story. But yeah, the idea would be that either the Willamette Falls actually progressed across the mouth. There's two possibilities. You know, the Willamette Falls could have actually eroded quickly enough to progress across the mouth of the Clackamas so that it went from being above the falls to below the falls. Or the mouth could have moved significantly north or south to do the same thing on its own, you know, through a landslide or something. I mean, there were several different options I looked at. None of them worked perfectly. That's why I'm a bit uncertain still. So it would require some pretty significant topographic, you know, gymnastics to get it to do it. But I don't know of another solution for why the incision is so rapid. There had to have been a dramatic change in base level. And that's the only thing I can figure out that it had to. I mean, the most likely culprit is that massive change in base level called the Willamette Falls. So how exactly it all works out, I was never able to come up with a really coherent story. So someone else can. I'd love to hear it, but I think it's got to be related, in my opinion. But
okay, two questions related to the dam, particularly River Mill Dam. What was or is the primary purpose of a river mill dam? Power generation, flood control, both? And then related to that, have there been any campaigns to remove any of the dams on the Clackamas?
Certainly from what I know about river mill, it's almost entirely power generation. There's no flood control ability to river mill. And actually not a lot of flood control ability for any of the dams on the Clackamas that I know of. North Fork maybe a little bit, but they just don't have sufficient storage relative to the flows of the Clackamas to do a lot in terms of flood control. That's not like, you know, Detroit Dam or something like that where there's significant flood control potential. So I don't think I could be wrong, maybe Jeff can correct me, but I don't think there's a lot of real flood management that comes into. I mean, there's certainly a lot more fish management that comes into the dams than flood management. And I don't know if there's I mean, when they've relicensed all the dams now, I think, and I don't think there's any any move to remove any of them because they're all relicensed now for 50 years. So unless something changes, I don't know that they would take them out. So I know, both River Mill, North Fork, all of those, I think all the licenses were renewed. So they're good for another 50 years or so.
So it was recently that they were renewed.
Yeah, I mean, Jeff might know the exact date that they actually issued the permit. Jeff, do you know the
2010.
actual date? 2010. Okay, yeah. So 2010 was the actual
2010.
license. Yeah, and so that's good for 50 years from that date, right?
Yep.
Yeah. So 2060 would be the soonest they would revisit that. Is that true of all of the dams, Jeff? Were they all done at the same time?
Actually, actually, Peter, it's a 40-year license, so it's 2050.
2050. Okay. And what, did they do all of them at once? I know they did North Fork, and North Fork was different though, didn't it? Wasn't that later?
Yeah, it was all part of the same development. There was the lower river, and then so North Fork and River Mill were in San Faraday. That was all grouped together as one, and then Oak Grove Fork was separately. They started off as two separate FERC projects, but then got just wrapped into one. So it includes everything from Timothy Lake all the way down to River Mill. And
so they're all basically were issued in 2010 and would be good till 2050.
That's right.
Okay. Yeah.
Okay. There's a question also related to the possible change of the mouth of the Clackamas. So it starts out based on the probable possible change of the mouth of the Clackamas River back when, does the 2007 Tigard Lake Oswego water diversion project have an effect upstream of the Gladstone intake related to water flow, erosion, other?
I'm going to have to punt on that one. I don't know enough about that particular system. Yeah, I don't. My knowledge sort of stops at the bottom of the Clackamas in terms of the way they operate that particular. Yeah, that's outside of my realm of knowledge. Sorry.
Anybody else on the call tonight that has a comment around that?
I can't say that I have any better information either, actually.
Upstream of Gladstone intake, yeah. Yeah, I'm happy to talk about it more afterwards or something. Yeah, but it's not immediately obvious that I would have any knowledge about that.
Okay. I believe that's the questions that were in the chat. Liz mentioned earlier, if you have a question and you haven't put it in the chat, send us a note that you'd like to voice that, and we'll invite you to do so.
Well, I'll talk for a second or so and see if any other questions come in. Oh, there is one. One question. I don't know if you see that.
Yeah, I can read. Yeah. So what was your study designed to find winnowing effect below the dam? It's like you spray paint rocks orange and then you sampled sediments. Yeah, we did a lot of things actually to figure that out. We did spray paint rocks. We actually tagged rocks with pit tags. We did lots of things to try and figure out what the transport was going on below there. But the primary data that was on the graph I presented was essentially a Woolman count, a spatial Woolman count, where we basically took a square meter of ground and we collected every single rock within that surface square meter and we measured every single rock. We also did linear Woolman counts of, I think we did 100 meters linear Woolman counts in some locations. So we did both. So an aerial Woolman count, which is just picking up the rocks and measuring their diameters, and then a linear Woolman count where you go every half meter or something like that and measure every rock and its diameter. So, and then you compile that into one data point that's an average for that location. Does that help? We also painted like squares, 1 meter squares of rock, and measured those, transport from those after flooding events. So we did lots of things to try and figure out, what was going on with sediment transport.
All right.
Oh, we did. There's another question about sieves. We did do a bunch of sieving of samples as well. But it was difficult because the grain size is so large. Your sediment size has to be huge in order to get a representative sample for sieving. My lab assistant can attest. He spent a lot of time sieving in the lab trying to do one sample because it was so large of a sample because the grain size, the D50 is so big.
I know that pain. Yeah.
Yeah.
So another question, back to the point that there's a potential of change of the river mouth from upriver of Willamette Falls to lower than the falls. Historically, there was a difference of salmon species in the Clackamas versus what was upriver based on steepness of the falls. So coho versus steelhead, because steelhead are much more adept swimmers than coho are. Oh yeah, are there any fish biologists that may be able to comment on that? That's interesting.
Yeah, I know we certainly had interesting discussions with the PGE fish biologists about the whole mouth theory and stuff. But
Yeah, I wonder if there's
there's
any
another
tribal
PhD there.
legend.
Yeah, I think
Yeah.
there's another PhD waiting for somebody to figure out the exact story down there.
And I do believe there will be future events of Journey Down the Clackamas that deal with fisheries. So stay tuned for that, those sessions.
Yeah, and we are, just about right on time. It's nearing 7 o'clock, which is actually 10 p.m. Peter's time. So thank you so much for such an excellent presentation. Our next session is going to be 2 weeks from tonight. That's June 29th. The presenter is going to be Mike Cole, and he's going to be building off of this geomorphology presentation and talking about the interaction of geomorphology and aquatic ecology. So how geomorphology kind of shapes all the bugs and or the populations of bugs and critters in the river system. So that's on June 29th. You can use the same Zoom meeting link, and you're essentially already registered. So we'll send a thank you email with these links. This presentation is recorded, and it will be loaded in the next day or two to our website, so you can watch it again there if you're interested. And feel free to use that Google Drive link if you are interested in continuing education units from Clackamas Community College, and that'll be the case throughout this webinar. So our thanks and appreciation for the wonderful talk this evening, and to all the participants who joined us. And we also want to thank our gold sponsors, Clackamas Water Environment Services and Clackamas River Water Providers and the Geological Society of the Oregon Country. So if you're motivated, feel free to click on our webpage and help support the conference and keep it free for everyone. So with that, I will say thank you, everyone, and we'll see you again on June 29th.
All right, thank you.
Thank you, Peter.
Yep.
Thank you so much.
My pleasure.
Thank you.